Okay, so there are a few main types of searching and sorting algorithms. Beginning with bubble sort, the most common and easy way to sort a list. So with the sorting algorithms, you want to find the fastest and shortest way to sort an unsorted list. So we'll begin by making a list, and we'll call it list, and it's of length n, and it's a list of integers. Now, how do we sort an unsorted list? Well, we use bubble sort. So we begin by defining the length of the list. So how many elements are in that list? Then we create a for loop that goes from 0 all the way to the end of the list. And as well, create another list, or another for loop. This for loop goes from the start to the ith term minus 1. So what does this mean? Well, let's say we have list is equal to 2, 7, 13, 4. So here we have 5 elements. And what we want to do is check, we begin with 2, and then we check onwards. So this is our ith pointer, and from there we use our j pointer. Alright, so what do we do? So we're checking j from 0 to n minus 1, n minus I minus 1. So I begins as 0, so n, or 5, minus 0, minus 1 is 4. So what does this mean? Well, it checks from 0 all the way to the 4th number. Okay, now from there, that already reduces the amount of calculation, or the amount of processes we have to do. From there, we check if the jth term is less than or greater than, in the j plus 1, or the next term. If these are, in other words, out of order, actually let's change this to actually make that make sense. So if these are out of order, then all we have to do is switch them. So this is what this line does. This line actually switches both values in kind of a dynamic way. Usually in other languages you would have to do you have to create a temporary variable that stores something and then switches it, but here we dynamically change it. So here we're saying that the jth term switches with the j plus 1, or the next term, and the next term switches with the previous term. So in this case, 7 would move to where 13 is, and 13 would move to where 7 is. And by the end of this for loop, you should have a sorted loop. So one more time, we go over the entire list with our ith measure, and then we only check from the beginning all the way to the end, minus however many we've already sorted. Why does that make sense? Well, we know that for every switch we do, we grow closer to a sorted list. So every single time I increases, so let's say I is now here, we know that we have now 2 more sorted numbers. So it's unnecessary to go over the entire list all over again. So let's say I is now 3, or sorry, 2. Then we can say search between these two and see if these have to switch. This portion here, that kind of moving end part. And that's where sort of the name comes from, because the unsorted number, let's say 2, or let's say 13, bubbles up or moves. Alright, now for binary search, any search algorithm is used to find a specific value without having to sort the entire list and then finding it with its index. Now, of course, we'll begin with the linear search, since it's the easiest one. All you do is you have a for loop, and this for loop goes through the entire list and checks whether that element is our target value, and then return. Otherwise, if this entire for loop works and it fails, then -1 is returned to say that there was no target value. This is a brute force way of doing it because you have an O of n. So as n approaches infinity, O of n approaches infinity, which is a very, very slow program. So we want to make that faster. So let's do this. Binary search, also called divide and conquer, relies on a central idea that you have an already sorted list. Well, we would begin at the middle term. So let's say we know this is of length 1, 2, 3, 4, 5, 6. This is of length 6 elements. So our middle term, here, let's make it an odd. Our middle term would now be 7. So we now want to check. Let's say our target is 10. What divide and conquer or binary search does is it begins on a middle term, the middle term, and then checks, is this value greater than or less than my target value? If it is less than my target value, and since we know that the list is already sorted, if it is greater than my target value, then we know we should move down. And why does that work? Well, basically, when it comes to search algorithms, you want to remove redundant searches. So if we know that our value that we are at right now is greater than or less than our target value, then we can disregard everything before it or after it. Because we know all of those values share the same attribute, that it's also greater than or less than that actual value. So we move from 7 to the middle of this. So we could say 2. Sorry, no, okay. This is less than. So we move to 10. Is this less than or greater than? Well, it's less than. So let's move one more time. Now we have a list between 13 and the end. So really, we can't do any other searches. Is it less than or equal to? It's equal to. So now we have that value. Now in programming, what you do is, while the lowest value or the end value of your search list is less than or equal to the highest value. What does that mean? Well, practically what you're doing is you're shortening or reducing the size of your list every single time you search. So you begin at this part. That means your search is between here and here now. And then you see, oh, well, it's less than. So we go to, let's say, here. Now your search is between here and here. So every single time your lowest point or the beginning of your new sublist changes. So this goes on until these become the same thing, or it becomes greater than, which would not make sense. Or of course you return that point. So here, we update the middle point every single time by finding the average between the two, and of course it's the whole number division because we don't want a decimal index. It doesn't make sense. Then we check that element at that middle point. Is it less than our target? Yes, then move our lowest point or the beginning of our sublist up by 1. Plus the middle point. So let's say it was here. We want to move from 0, so here, plus all the way to the middle point, and plus 1. So now that we're checking from here all the way to the end of the list. Otherwise, if it's greater than or equal, then we want to move from 0 to the middle minus 1. So then we're instead searching from here. So instead, our highest point, searching from 0 all the way to here, right? Because we haven't updated our lowest point yet. Otherwise our else statement handles any other case, which means that our element is actually the target, which means you can just return the middle point or the index of that. Now for selection sort, it works similar to bubble sort, but different enough that it makes it a different type of efficiency. So here, and now for selection sort. So we begin with this, and it's 1, 7, 4, 13, 9, 12, 15. So we can see here that this list is of length 1, 2, 3, 4, 5, 6, 7. So we can see here that this list is of length 1, 2, 3, 4, 5, 6, 7. Alright, now how does this work? Well, selection sort has two sort of pointers, you could say. So we begin by pointing at the smallest number. So we begin by pointing at I, or the 0th number, and then we have a moving pointer that compares. So this moving pointer begins at the same index, but then moves to the next one. So here, this is where it starts. So the purple here is our main index. Starts at I, and then we create another pointer j begins from I plus 1, so the number after I, all the way to the end of the list. So how does this work? Well, every single time it is checking whether this value that j is taking on is less than our minimum value. So let's actually do that. Here we have minimum value as 1. Then we check 7, less than 1, no. Nope, 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 yeah. So what happens here? Once it finds that smaller value, it says that our actual minimum index, or the index of the minimum value, is actually j. So right here. And then we swap these two values so that they're in from least to greatest order. And now this is repeated for every value. So once you've done that, you can say this has been sorted and this is now switched. So this becomes a new list where it's -12, 7, 4, 13, 9, 1, 15. And then again, so we begin at 7 and our moving pointer goes from 4, 13, 9, 1. Now we switch those. So now we have a new list. It's -12, 1, 4, 13, and this goes on until the entire list is sorted. Insertion sort works a bit differently, but again, a lot of these sorting algorithms are similar to one another. So knowing one of them is beneficial for learning the other one. So again, also, it's important to note that it has multiple names. So quick sort, heap sort, merge sort, all of these have similar names, or multiple names. So knowing all of them is helpful. Now here, we begin at the first, or the second number, and go towards the end. And then we create a key variable that has the ith term as its value. We make a new term, j, which is always I minus 1. Then this while loop continues going while the jth term, or j, is not greater than or equal to 0, because it get incremented by 1 every single time, and the key term, so this ith term, is less than our jth term. If they are, you set them equal. In every loop, you set the neighboring term with the current term. You increment j by -1, and then you make j plus 1 equal to the key.